If you already know the basics of scikit-learn, but you want to be more efficient and get up to date with the latest features, then this is the video for you. My name is Kevin Markham, and I've been teaching machine learning in Python with scikit-learn for more than 8 years. Over the next 3 hours, I'm going to share with you my top 50 scikit-learn tips, including how to tune a pipeline, visualize a decision tree, plot an ROC curve, speed up a grid search, use feature selection, create an estimator diagram, build a custom transformer, use stratified sampling, build an ensemble, and so much more. Each tip ranges from 2 to 8 minutes, and you can use the timestamp links in the description below to skip along if you're already familiar with that particular tip. All of the code is on GitHub if you want to follow along, and that link is below as well. With that, let's get started with tip number 1. Scikit-learn tip number 1. Using ColumnTransformer to apply different preprocessing to different columns. So this is a very common need, and ColumnTransformer just makes it highly convenient, specifically for selecting from a data frame and specifically for selecting columns by name. So this is new in scikit-learn 0.20. And in the example, we've got here a 4-column data frame called X. And we're going to go down and do some imports and create some instances of one-hot encoder and simple imputer, and we'll talk in a second what those do. And then here is the heart of the tip. It's about using ColumnTransformer, specifically the make ColumnTransformer function, and we're going to pass it 2 tuples. The first tuple is this one, the second tuple is this one, and then we'll pass it one more argument. So the first tuple is about one-hot encoding embarked and sex. So those are categorical columns. We're going to one-hot encode them, which is the same as dummy encoding. And there are 3 possible values for embarked. So it shows up as 3 columns once one-hot encoded. There are 2 possible values for sex, so those show up as 2 columns. So one-hot encoding of these 2 columns. Then I want to do a imputation, meaning imputing missing values, filling in missing values, of the age column, because you can see the age column has 1 missing value. By default, it imputes the mean value of that column. And here we go. You can see the 31.2 is the mean of the 5 other values. And finally, we've got the remainder argument, which says I want to pass through other columns. So basically, whether you have 4 columns or 400 columns, you're going to specify some columns, and then you have to tell the ColumnTransformer what it should do with the remaining columns, meaning all columns you did not specify here. So in this case, we want to pass through the remainder, which means essentially don't transform the remaining columns I didn't mention, which in this case is just fair. Go ahead and pass it through untransformed. The other option would have been drop, which means just ignore it and don't include it in the output. So fit transform is how you run the transformation, and here's our output. Notice the ordering. It's in the exact order specified within the ColumnTransformer. Embarked and sex, one-hot encoded, age, imputed, and the remainder at the end. So that's the ordering. It has nothing to do with the ordering in the data frame. It's about the ordering you put it in the ColumnTransformer. And this here is the feature matrix that's going to get passed to a model or further transformed. Tip number 2, there are 7 ways to select columns using ColumnTransformer. So in tip number 1, we selected by column name, but there are a bunch of other ways. Let's take a look at our example. So we've got the same 4-column data frame. Now, make ColumnTransformer, which I showed you above, came out in 0.20. Another thing we're going to use in this tip is make column selector, which came out in 0.22. So our goal is to use make column transformer to select these two columns and one-hot encode them, and this will be the end result. And what I'm showing you here is that there are 7 different ways to do that, and they all serve different needs. Now, before I show you these 7, I just want to mention that remainder equals drop is actually the default, so that's why you don't see fair and age get passed through, because remainder equals drop is the default. Okay, so here are the 7 methods for selecting these two columns. The one we've already seen is selecting by data frame column name, so I just say embarked in sex. The next option, option 2, is to select by integer position, so this is position 1 and position 2. It starts at 0, 1, 2, 3. Now, this is super useful if your input is not a data frame, because your input to make column transformer, when you do the fit transform, does not have to be a data frame. It can be a NumPy array, and those don't have column names, so you could specify by column position, okay? The third option is a slice, so I want column 1 through column 3, and like all slices in Python, it is inclusive of the first value and exclusive of the second value, meaning I want columns 1 and 2. Now, this would be super useful if I have like 100 columns in a row that I want to select. I would just say slice 1, 101. All right, your fourth option is Boolean value, so I can say false, true, true, false, and it will select those two columns. The use case for this is less clear to me, but maybe you can create a condition on the columns attribute and come up with this. There are probably different use cases I haven't thought of. The fifth option, and all the rest are going to use this make column selector. The fifth option is to use a regular expression pattern with the column names. So you say pattern equals, and I say this is a regular expression. I want anything that includes E or S. All right. So capital E or capital S, because regular expressions are case sensitive, and that includes only embarked in sex. Now that's kind of a silly example, but you can imagine you had 100 columns and 10 of them have some particular like starting or ending value, and you match on that because those are the columns you want to select. The next is dtype include. This is I want to include object columns only, or I want to include object columns and some other type of column, and it selects only the object columns. So this is useful if, say, you want to one-hot encode all object columns. And the seventh option is what data types do I want to exclude? Let's say you want to transform all except for object columns or all except for numeric columns. You can do that. So with a pandas data frame, you can use any of these 7 options. With a NumPy array, I think you can only use options 2, 3, and 4. Okay? Tip number 3. What is the difference between the fit and transform methods? Fit is when the transformer learns something about the data. Transform is when it uses what it learns to do the data transformation. Okay, so in scikit-learn, you're going to use fit and transform a lot. Sometimes you'll be using it explicitly, meaning you're going to be running the fit and transform methods. Sometimes scikit-learn is going to be doing it on your behalf under the hood. It's easy to treat fit and transform as a black box, but you will be much more effective in using scikit-learn and reading the documentation and learning new features if you actually understand what fit and transform are and why they are different. Now, I do want to say that this only applies to transformer objects because models do not have a transform method, only a fit method, but transformer objects, which are ones that do data transformations, have a fit and a transform. Okay, so in summary, fit learns something about data, and transform is when it uses what it learns. Now, I've got 4 examples of that, of what fit does versus transform in that particular case. If you're not familiar with these, I can't teach them briefly. I could spend an hour on each of these to get you really familiar. The point of the examples is if you happen to be already familiar with one or more of these. Probably the simplest example of the four to understand without any background knowledge is simple imputer. Simple imputer is for imputing missing values, meaning filling in missing values. We saw this back in tip number 1. So what happens with simple imputer? Well, fit step is when it learns the value to impute. So it learns that the mean of the column is 31.2 or whatever it was. And transform is it when it uses that value to fill in the mean. Okay? So the fit step is when it learns the value it's going to fill in, and the transform step is when it actually fills in the value. So you might ask, why are fit and transform separate methods? Couldn't it do it all at once? Shouldn't it do it all at once? And that's a great question, which is answered by tip number 4. Tip number 4, use fit transform on training data, but transform only on testing/new data. This is crucial, okay? So let me clarify a few terms and then I'll kind of explain this in more depth. First, when I say testing data or new data, testing data means like data resulting from train test split, for example. New data means truly new out of sample data where you don't know the target value, where you don't know the label. Okay, that's the distinction I'm drawing, but it really doesn't matter because you apply the same workflow to both cases. The other thing I want to clarify is fit underscore transform is a method you call that runs a fit followed by a transform. Okay, it runs the fit, then it runs the transform. But it's more computationally efficient than running a fit and then a transform as separate method calls. So fit underscore transform is a single method call. It's more efficient than running fit and then running transform on the same object. You can do that, that's fine. It's just slightly less efficient. So on training data, you should use both. On testing or new data, you should only use transform. You should not use fit. Now, why is that? Because it will apply the same transformations to both sets of data. Let me give an example. If you're running one hot encoder on that embarked column we saw in our X data frame, it will learn the columns C, Q, and S from the training data, and it has to create those same columns C, Q, and S for the testing data. But let's pretend our testing data, our new data, only has the Q value. You still need one hot encoder to create the same 3 columns, and you still need Q to be represented by the middle of those 3 columns because your training and testing data need to have the same number of columns, and they need to mean, those columns need to mean the same thing. So that's what I mean by it creates consistent columns. Let me give you another example of all of this. Let's say the imputer learns a mean of 31.2 from training data. Well, it will fill in 31.2 if that value is missing in the testing data, okay? So simple imputer does not take the mean of the testing data and fill that in. Okay, so the point is you use fit and transform on your training data to learn that mean age of 31.2 or whatever it was. But when it comes to your testing data and you run transform only, that says don't relearn a mean from the testing data. Instead, fill in the mean that you learned from the training data. If you did instead fill in the mean of the testing data, that would be what is known as data leakage, which basically means learning something new from the testing data. That is not allowed because it doesn't properly simulate reality. And simulating reality is the whole point of model evaluation. You're supposed to pretend that some data is new. You do train test split and you pretend that the test data data is new data. You can't learn something new from it. So that's called data leakage, and data leakage results in inaccurate model performance estimation. And the whole point is I want to estimate the performance of a particular model without actually having new data, okay? Tip number 5. Okay, these are 4 reasons to use scikit-learn, not pandas, for ML preprocessing. So let me walk through each of these one by one. I will say I'm talking specifically about preprocessing data for machine learning. You know I love pandas, and it still has huge uses for working with data and data exploration, but my point is about machine learning preprocessing, meaning taking raw feature values and making them suitable for machine learning models, okay? So let me briefly unpack these 4 points as to the case I'm making for scikit-learn. Point number 1, you can cross-validate the entire workflow. What does that mean? Well, that means you can create a pipeline of pre-processing and model building, and you can use cross-val score on that pipeline. Cross-val score will take in the pipeline and it will do the splitting and pre-processing, but it will do the pre-processing within each fold. It will not do the pre-processing first. That actually produces the most accurate estimates of future performance. If you do the pre-processing yourself before cross-val score, that leads to data leakage. Instead, you want to create a pipeline of pre-processing and model building and use cross-val score on the pipeline. Okay. Point number 2, you can grid search model and pre-processing hyperparameters. So grid search is normally used for searching model hyperparameters, like, for example, the C-value of logistic regression, but you can also use it to search pre-processing hyperparameters, for instance, the imputation method. So how that works is you create a pipeline and then you do a grid search of the pipeline, and I'll show you that in a future tip. And with pandas, you just simply can't build a pipeline, so this functionality is not available. Reason number 3, avoids adding new columns to the source data frame. So if you were doing some dummy encoding using pandas, for example, and the column you're dummy encoding contains 20 categories, you're going to get 20 new data frame columns. You can do that, but that's super inefficient in terms of space, and it makes the data frame harder to explore when you keep adding more and more and more and more columns. Instead, I'm recommending you use ColumnTransformer, and that allows you to not affect the source data frame. And finally, reason number 4, pandas lack separate fit transform steps to prevent data leakage. So, as we've talked about, scikit-learn has fit and transform so you can learn something from the training data and apply it to both the training and testing data. It would be extremely complicated in pandas to duplicate this. Of course you can do it, but it would be so much code. I'm thinking 10 times as much code, and it would be way more complicated. Pandas is simply not built around a workflow of splitting data, learning something from one piece, and applying it to both pieces, especially if you wanted to do something like cross-validation. This workflow would be absurdly complicated to do in pandas. Okay, so that's my brief unpacking of these 4 points. The point of all of this is I'm making the case now for if you are doing machine learning, you are best served by learning how to do your pre-processing in scikit-learn and not in pandas. 2 common ways to encode categorical features: one hot encoder for unordered, also known as nominal data, and ordinal encoder for ordered or ordinal data. And we'll come back to this statement in a bit, but here's our example. So we've got this data frame. Shape is an unordered feature, meaning there's no logical ordering to the categories. Because of that, we're going to use one hot encoder, and here we have one hot encoder. We pass it shape, and it generates 3 columns because there are 3 possible categories of shape. One hot encoding is the same as dummy encoding. This left to right order is alphabetical, thus this represents circle, this represents oval, and this represents square. Now, you could use getDummies in pandas to do this, but one hot encoder integrates much better into the scikit-learn workflow, meaning pipeline, meaning cross-validation, meaning grid search. So one hot encoder is definitely the way to go rather than getDummies. Okay, so that is our unordered data. Our ordered categories are class and size. So by ordered, I'd mean there is a logical ordering within each feature that may have a relationship with the target. And I'll give an example in a bit. But with class, we see first, second, third, and what we do is we define the ordering of the categories when we create our ordinal encoder instance. So first before second before third, and then for this size feature, we say small, medium, large, and extra large. Then when we use ordinal encoder, it encodes each feature as a single feature. So you can see that first gets encoded as 0, second gets encoded as 1, and third gets encoded as 2. And then same here, small, medium, large, extra large becomes 0, 1, 2, and 3. Now we included M for medium in this data, even though it doesn't appear as a size, because we know it will occur in the data. So it makes sense to include it. Now, when we have ordered data like these, this ordinal encoder is the optimal scenario because the model can learn that relationship between it increasing or decreasing and the target, okay? So let me give you an example that might help. So let's pretend we're predicting airplane ticket price, and class is one of the features. Okay, we want the model to be able to learn that increasing the class value decreases the price. In other words, first class tickets are the most expensive, second class tickets are the second most expensive, and third class tickets are the third most expensive. By using ordinal encoder, we can encode that as a single feature, and the model can learn, okay, as the class number goes up, the price goes down. So it learns that inverse relationship. If you were to use a one-hot encoder for class, meaning dummy encoding, it could still learn that relationship in a way, but it would only learn the relationship between first class and not first class. So if you dummy encoded this, it would be 3 columns, and it could learn, okay, when you have first class and not first class, here's the impact on the price, but it will result in a better model if you encode it as a single feature using ordinal encoder. Okay, let's go back to label encoder. And I said label encoder is for labels, not features. So label encoder is designed for class labels, okay? It works very similar to ordinal encoder. So label encoder and ordinal encoder work similarly, except with label encoder, you can't define the ordering, and you can only encode one thing at a time, whereas with ordinal encoder, you can encode multiple features at a time. Thus, label encoder is not useful for features, and scikit-learn docs recommend against using it for features. They explicitly recommend against it. So ordinal encoder is for features, label encoder is for labels. And in fact, just as a side note, all scikit-learn classification models that I'm aware of can accept string values as the labels, so you don't actually need label encoder usually. So the use cases for label encoder these days are quite limited. Tip number 7, for a one-hot encoded feature, what can you do if new data contains categories that weren't seen during training? So you can set this handle unknown equals ignore. It will encode all new categories as zeros. Now, this is specifically useful if you don't know all possible categories that might ever appear. If you do know all possible categories, just specify those categories when creating your one-hot encoder, and it will create a column for every category. Okay, so let's see our example. We've got this data frame with one feature. It knows about 3 values, so it creates 3 columns with the one-hot encoder. In our new data, it sees a new value D that it has never seen. So because we set handle unknown equals ignore, you get these 3 zeros, okay? If we had not set handle unknown equals ignore, it would just error out. So that's our alternative. Now, this strategy of setting all unknown categories as 0 is effectively like treating all unknown categories as an other category. Now, it does mean that all unknown categories, such as E or F or G, will all be treated the same way. But ideally, what you'll do is you'll set handle unknown equals ignore, and then later you'll go back and retrain your model to include the previously unknown categories. You might ask, would this actually ever occur? And I know the answer is yes. Like, just because you have unknown categories, that doesn't mean you have bad data. So maybe you have a feature in your model that is US political parties, and there are tons of tiny political parties, and your current data set has 100 different political parties. But, every week some new political party shows up, and it just ends up in your data set, and your trained model doesn't know anything about it. But that's reasonable. Like, you can go back and add it to your model in the future, but for now you still want to make predictions even though you've got this category you were never familiar with in advance. Okay? I'm sure some of you aren't 100% comfortable with this option. Just to put it out there, your only other option is to leave it at the default of handle unknown equals error, and just don't make a prediction when you see new categories. So if you're okay with not making a prediction and just erroring out, then that's fine. But this is a good alternative. One other thing I wanted to mention about this is that in small data sets, when you're using train test split or cross-validation, this issue will often occur because you can imagine if a category is infrequent, it could appear in the test data but not in the training data, which will cause an error if you're not handling unknown. Tip number 8. What does pipeline do? It chains together multiple steps. The output of each step is used as the input to the next step, and this makes it easy to apply the same preprocessing to train and test. So let's walk through this example. We're going to create our imputer and our classifier, which is logistic regression. Then we're going to use make pipeline to create a 2-step pipeline in which first we impute missing values, then we pass the results to the classifier. Okay, so here is our training set. It has labels, of course, and it has one missing value. Here's our testing data, no label. It has a missing value in feature 2. We're going to define those 2 features. We're going to set our x and y from train, and x new is from test. And then when we use pipeline, when we say pipe.fit, it's kind of like model.fit, or in this case, clf.fit, except it runs the pipeline. So first, your x data goes to the imputer, and it does the imputation, passes the result to the classifier, and the classifier does classifier.fit xy, but it's the transformed x, not the original x. Okay. Now, when we do pipe.predict, it takes x new, which is this data, and it runs the imputation by using the pipeline, and it uses the imputation values it learned during fit, which is important for preventing data leakage. It uses those imputation values, then it passes the transformed x new along to the predict method, and the model.predict runs with the transformed x new. Okay, so I know that's a lot to take in, but you'll see more about pipeline in future tips. This example demonstrates 2 of the benefits of pipeline. One is just the simplicity of code that results, and the second is that it prevents data leakage. Other benefits not shown here, but you'll see in future tips, you can cross-validate a pipeline, which is important. You can do grid searches on a pipeline and not just a model. Couple final notes about pipeline. A pipeline in this case is a pre-processing step ending with a model. You can also do a pipeline that is only transformations and just results in data transformation. Final thought is I use make pipeline because it doesn't require me to name the steps. Whereas if you just use pipeline with a capital P to create your pipelines, it does require you to name your steps. It's a lot more typing. It's harder to write. It's harder to read, in my opinion. So I always use make pipeline, and I'll show that more in a future tip. Scikit-learn tip number 9. When imputing missing values, you can preserve info about which values were missing and use that as a feature. Why? Sometimes there's a relationship between missingness and the target or label you are trying to predict. So here's our example. We've got our data frame, missing value. We're going to use our simple imputer. By default, simple imputer imputes the mean value. So that's why it takes the mean of 20, 30, 10, and 10. That's 17.5. It inserts it. So that's how simple imputer works. If you add this add indicator equals true parameter or argument, it will add a second column that the whole point, it's called an indicator matrix. It puts a 0 if the value is not imputed and a 1 if the value was imputed. So it's telling you what values used to be missing. Now let me give an example of why you might do this. Let's pretend you're predicting the presence of a disease. And you can imagine a scenario in which a missing age is a good predictor of disease. Because let's say we don't have age records for people in poverty, and poverty is a good predictor of disease. Thus, missing age is a good predictor of disease. Okay, so these values, it turned out in this scenario I'm proposing, are not missing at random. They're missing for people in poverty, and poverty is a predictor of disease. So missingness is a predictor of disease. So that's kind of an example of when this might be useful. Now, missing value handling is a gigantic topic, and I cannot universally recommend that you should even impute values. There are other alternatives. You can drop rows that have missing values. Well, if they're in training, in test, you're kind of stuck. You can just not use features that have missing values. If you do impute values, there are other methods than simple imputer, such as KNN imputer and iterative imputer, that'll probably produce better results. I'll handle those in future tips. If you don't want to impute missing values, but you do want to have this indicator matrix, you can do that. There's something called a missing indicator class that's available in scikit-learn. In all cases, it's super important that you understand your data really well, why it's missing, and then talk to domain experts if possible to figure out what's going on in your data before you blindly do things like imputing values. So, huge topic. I can only say so much in a short tip. Tip number 10. Why set a value for random state ensures that a random process will output the same results every time, which makes your code reproducible by you and others. Okay, so here we've got train test split. We've got a data frame with only 6 rows. We have train test split. We set random state equals 1, and we get this split, which pulls out rows 0, 3, and 5. If we do the same random state again, so random state 1, we get the same random split, 0, 3, and 5. But if we do random state equals 2, we get a different random split, 2, 5, and 0. So setting a random state is also known as setting a random seed. This applies outside of scikit-learn. There are definitely instances in pandas and scipy and other libraries where you set a random seed. The method varies in scikit-learn. It just has this argument called random state. Anything that uses random state is a pseudo-random process. Computers can't do randomness. Computers can do pseudo-randomness, meaning they're approximating randomness. And by setting a random state, you're allowing the result to be reproduced, which is important if you want to show your results to others, because you could do this train test split, get an accuracy of 80%, do this train test split, you get an accuracy of 78%, and you say to your coworker, wait, I swear I got 80%. Well, if you're not setting a random state, you're going to get a different result every time, whereas if you do set a random state, you'll get a consistent result, which is important. Final point, if you're wondering, random state is used all over the place in scikit-learn. I don't have an exhaustive list, but a few things I could think of. It's used with a support vector classifier. It's used with logistic regression for some of the solvers. It's used with randomized search CV, used with random forests. So all over the place it's used. Scikit-learn will not throw a warning if you don't use random state. But I would encourage you, if there is a random state, you should use it. And the only way you're going to know there's a random state is by looking at the docstring or looking at the documentation. So you need to know about random state. Doesn't matter which value you pick. Just pick a positive integer and use it. There are two imputers, namely KNN imputer and iterative imputer, that you can use in replacement of simple imputer for missing value imputation. So let's take a quick look at the example. We've got this data frame, and in red you can see that the age value is missing for one of the rows. We're going to try iterative imputer, and when we fit transform, it imputes this value, and KNN imputer, we're going to set this n neighbors equals 2, and we fit transform, and we get a different value. But the point is, it did imputation in a different way than simple imputer. So why is this notable? Well, simple imputer, which I didn't demonstrate here but have shown previously, is univariate, meaning that it only takes a single feature into account. So if you used simple imputer on age, it would either take the mean or the median or the mode of age, and that's it. But that's quite a blunt approach. What if, for example, age was well correlated with other features? So for example, what if there was a correlation between fair and age such that people with lower fairs were also younger and higher fairs were also older? It would make sense to impute low age for low fair values and high age for high fair values. So that suggests a multivariate approach, which just means it takes multiple features into account. So both iterative imputer and KNN imputer are multivariate approaches. Now, in case you're interested, I'm going to actually explain how these two things work because I think it's super interesting. So iterative imputer, let's pretend we've got three features and we'll call them, just for simplicity, A, B, and C. And C has a missing value, okay? So here is how iterative imputer works. For all rows in which C is not missing, so for these 5 rows, scikit-learn trains a regression model. It uses A and B as the features and C as the target. And then for all rows in which C is missing, it makes predictions for C by passing A and B to the trained model. So in other words, when you use iterative imputer, it actually builds a regression model with 2 features and 1 target, and then it makes predictions on any places where there are missing values using the regression model it has built, and those predictions are the imputed values. Now, you can actually choose which regression model is used by iterative imputer. I didn't choose it here, but the most important thing, the model used by iterative imputer is independent of the model you are training with this data. So you don't even have to be working on a regression problem. The model used by iterative imputer is totally independent of the model you are using with this data set as the training data. Okay, now let's talk about KNN imputer. So with KNN Imputer, again, we've got features A, B, and C, and I've set n neighbors equals to 2, and here's how that works. Let's pretend we have a row in which C is missing, so that's this row before it was imputed. So scikit-learn finds the 2 most similar rows measured by how close the A and B values are to this row, okay? So this row has a missing value. So scikit-learn says, wait, what are the 2 closest rows to it? Well, that's this row and this row, because they both have a 0 in the first column and around an 8 in the second column. Those are definitely closer using a distance metric. So what it actually does is it takes those 2 rows that are the closest and it averages the C value. So 26 plus 35 divided by 2 equals 30.5. So that is what gets imputed. Now, the natural question is, how do you choose n neighbors? Well, you just treat that as a pre-processing hyperparameter that you should tune. Okay, a couple more things. So you might be wondering, which features are taken into account by iterative imputer and KNN imputer? Well, any features that you pass to the imputer are taken into account. So by passing these 3 columns to the imputer object and doing the fit transform, it's going to look for missing values in those 3 columns and use the other columns to help impute, okay? Now, each row, in case you're wondering, can have multiple missing values, and each feature is allowed to have multiple missing values, and there's logic for how both of these imputers handle all those different cases in kind of a sophisticated fashion. Final thing is, to my understanding, both of these can only impute numeric values and can only take numeric features as input, so you can't use them to impute like a categorical variable, and it can't use categorical variables as direct input. Scikit-learn tip number 12. What's the difference between pipeline and make pipeline? Well, pipeline requires naming of steps, make pipeline does not, and the same applies to column transformer versus make column transformer. So let's see an example. And here are my examples. So the blue is, of course, the make versions, and the red is the, quote, non-make versions. So let's talk about these. With make column transformer, you pass it tuples. So I'm passing it 2 tuples, and those tuples are separated by commas, and then any arguments you just put at the end. So the tuples are length 2, so you have your object and then your list of columns that object should be applied to. And then for the pipeline, it's very easy to see. With make pipeline, you just pass your objects, so your transformer and model objects, okay? Column transformer and pipeline are, as you can see, more code. So with column transformer, you pass a list of tuples, and the tuples are length 3, and each tuple has a transformer name, transformer object, list of columns, same thing. You are making up these names, okay? So those names are your choice. With pipeline, instead of just passing the objects, you pass a list of tuples, and within the tuples, you define the step name, and then you pass the object, step name, object, okay? So all of these names, encoder, imputer, preprocessor, classifier, are all your choice. Now, personally, I use the make functions. I find them easier to read, easier to write, easier to debug. These ones have way too many brackets, parentheses, and commas. Even simple transformers and simple pipelines, I get thrown off by all of the different brackets and commas and whatnot. Now, when you use the make functions up here, the transformer names or step names actually get assigned for you. And normally that's not a problem. Now, if you are doing a grid search of hyperparameters, either of the pipeline or the transformer, the custom names can be useful for clarity. One final note, column transformer versus make column transformer. Column transformer enables something called transformer weights, meaning you can do feature weighting. I'm not clear on the use case of this, but it is important to know that's one less function you have available to you with make column transformer. Tip number 13. How do you examine the intermediate steps in a pipeline? Use the named steps attribute. Let's take a look at this example. We've got 2 feature columns, 1 target column, and you'll note there's a missing value in the age here. We're creating a pipeline of simple imputer and logistic regression. And then when you fit the pipeline, we're passing it X, which is these 2 features. And it's useful to note that age and p-class are getting passed to the simple imputer. It's imputing any missing values, and that transformed version of X gets passed to the logistic regression model for fitting. Okay, so that's what happens when you do pipe.fit. It actually has quite a long output, so to save on screen space, I just used a semicolon at the end. That's a little IPython trick for suppressing output. And IPython is the kernel used by the Jupyter Notebook. Okay, so let's get to the meat of this, which is name.steps. So I've done the fitting, and I want to inspect the imputer that was in the pipeline and the logistic regression model that's in the pipeline. I access it by named steps. So I do pipe.nameSteps, and then I select the simple imputer step, and then I can access its statistics attribute. And what is that? This is actually the mean of each of these 2 columns. The mean by default is used for imputation by simple imputer. And even though there's no missing values in p-class, it collects the mean of p-class in case you have any missing values to impute in the new data, even though there weren't missing values in the training data. Now, how did we know the name simple imputer? Well, the first way, you could just type pipe.nameSteps and it'll show you the named steps. But we know it's called simple imputer because when you use the make function, it by default just uses the lowercase version of the class. So instead of simple imputer with capitals, it's just simple imputer all lowercase. If I was using pipeline instead of make pipeline, I could define this name myself. Now, we can also access the logistic regression object and its coef attribute. So these are the model coefficients, and for what it's worth, what we're seeing is that an increase in age slightly increases the likelihood of survival. An increase in p-class decreases the likelihood of survival. You'll understand that if you're familiar with logistic regression and how that works. Tip 14. 4 options for handling missing values, also known as nans. Number 1, drop rows containing nans. Number 2, drop columns containing nans. Drop 3 is to fill the nans with imputed values. And number 4 is use a model that natively handles nans. And that is new, and that's really the focus of this tip. Now, just to point out, number 1 and number 2, the downside of those is that you're losing data that is possibly valuable, and the downside of option 3 is that you are, of course, just making up data. So option 4 is actually the ideal option. So let's see our example. We've got a data frame I'm calling train and one that I'm calling test. I'm using a little pandas trick to count the number of nans in each column. In our training data, age has missing values. In our testing data, age and fair have missing values. Down here, I'm going to remove that survived column from train, move it to a separate series called label, so that train is 3 columns rather than 4. So I am enabling this experimental hist gradient boosting classifier. Okay, and we're using this because this is the one classification model in scikit-learn that has native support for missing values, meaning it can handle them without doing any imputation. Okay, so this model actually came out in 0.21, but 0.22 is when it developed native support for missing values. So we create an instance of it, and we do a fit on train and label, and a predict on test, and it makes predictions. And you might be thinking like, wait, what is this? Like, what's the point? And the answer is there were no errors, because remember, every other scikit-learn model, if you try to put any missing values in there, it will error out. And you might be thinking, wait a minute, is it just doing imputation? And the answer is no, and that's the big news. It is not doing imputation. These missing values are still there. It doesn't pretend they're different values. It just has a way for handling them. Now, I haven't studied this model, so I can't explain in depth how it handles them. You can read the documentation if you're really interested. But the point is, it's not doing imputation. It's figured out a smart way to handle missing values without filling them in or dropping rows or columns. Okay? One final note, there is a hist gradient boosting regressor if you need this functionality with a regression problem. Scikit-learn tip number 15. My most controversial tip of the week. In most cases, I recommend that you don't use drop first with one hot encoder. Here's why. So let me first start by explaining the context here. So what is drop equals first? Drop equals first is a one hot encoder option that drops the first level of each category. Now, this is acceptable because no information is lost, and that's because the first level of any category, or one level of any category really, contains redundant information. Now, why would you do drop equals first? If you ask the scikit-learn folks, or just read the scikit-learn documentation, it just says, quote, "This is useful in situations where perfectly collinear features cause problems, such as when feeding the resulting data into a neural network or an unregularized regression." So what I just read you was the reason to use drop equals first. So I am advocating not to use drop equals first in general. And let me explain why. Reason number one, multicollinearity is rarely an issue with scikit-learn models. Well, most of the time, you're not feeding the results into a neural network or an unregularized regression model. In other words, the multicollinearity caused by not dropping the first level doesn't matter in a meaningful way to most scikit-learn models, okay? So to me, why drop a level if it's not providing any performance benefit, okay? Reason number two, drop equals first is incompatible with handle unknown equals ignore. Well, handle unknown equals ignore encodes unknown categories seen in your new data. It encodes them as all zeros. Drop equals first will encode your first category as all zeros. You don't want to encode them both the same way, so scikit-learn doesn't even allow it. All right. And then reason number three, not to use drop equals first, it may be problematic if you standardize all features or use a regularized model. All right, this is super complicated, and if you don't already understand standardization or regularization, this is going to probably fly way over your head. But let me try to walk through it. If you are going to use standard scalar on all of your columns, including your one hot encoded columns, it doesn't seem right to me to do standardization after dropping a level, because it feels to me like the thing you dropped should be standardized too. So it was okay to drop because the first level was redundant, right? Like that is the theory behind why dropping a level is allowed. But once you change the numeric values of the other levels, the level you dropped no longer seems like redundant information, okay? So one solution is just to use standard scalar on the other columns, but not the one hot encoder columns. And that's what most people do in general. They one hot encode certain columns and they use standard scalar on other columns, which to me is acceptable. Okay. Now let's talk about regularization, which is common in scikit-learn models. If you pass one hot encoded columns to a regularized model, regularization is no longer going to work properly if you've dropped a level. And it's kind of similar reasoning. The dropped level is no longer redundant information once you shrink the coefficients of the other levels. So if it's no longer redundant, then that tells you you shouldn't have dropped it, or rather, don't use a regularized model, but regularization is useful and it's all over the place in scikit-learn. So that's why I'm advocating in general, don't use drop equals first. And just to clarify, I started this tip with in most cases. So if you have a particular reason that you believe you should use drop equals first, then by all means do it. I'm just saying let's not do it as a community unless we have a reason to do it. You can cross-validate and grid search an entire pipeline. The preprocessing steps will automatically occur after each cross-validation split, which is critical if you want meaningful scores. Okay, this is a big one. Let's start with the basics. Quick recap, what is cross-validation? It is a model evaluation procedure that simulates model performance on future data. So we want to know how a model is going to perform on new data in the future so that we can choose between models today. Now, it has some inherent limitations, namely that we are assuming the future will be just like the past, but despite its limitations, it is a super useful tool when used properly. Okay, so let's move on to the code here. We are doing some pre-processing using one-hot encoder and count vectorizer. We are using a logistic regression model. We make a column transformer, one-hot encode the sex column, vectorize the name column. We make a pipeline of our column transformer and our logistic regression classifier. Okay, here's the first big piece. We're going to cross-validate the entire pipeline. So we will actually pass the pipeline to cross-val score, not just the model. So here's what happens when we do that, and this is the critical piece. First, cross-val score splits the data into 5 pieces. 4/5 is designated the training data, 1/5 is designated the testing data. On the 4/5, it uses the column transformer to prepare the data, and then it trains the logistic regression model. On the 1/5, it uses the column transformer to prepare the data, and then it makes predictions using the trained model. Then it evaluates the accuracy of those predictions. Okay, all of that occurs one time in cross-validation, and then it repeats that process 4 more times. So we get 5 cross-validation scores, and then we take the average of those scores. Okay, so why is this so important? Why am I telling you all of this? Here is the key point. The key point is that cross-val score splits the data and then applies the pipeline steps. That results in more reliable or meaningful scores than the alternative, which is pre-process the data and then use cross-validation on just the model. Okay, the alternative I'm not showing because it's not the right way to do things is to pre-process all of your data first and then pass the pre-processed data to cross-val score and just pass the model object to cross-val score. Now, why is it better to cross-validate a pipeline in which the pipeline will take care of the pre-processing? Well, it's complicated to explain, but in short, pre-processing before splitting the data doesn't properly simulate reality. Splitting then pre-processing does simulate reality. And the whole point of cross-val score is to simulate the future reality so that we know how the model is going to perform. Okay, so in other words, do what I'm showing you here and you will be better off. Okay, there's even more to this tip, if you can believe it. So we are going to use grid search to find optimal tuning parameters for the pipeline. Now, normally you use grid search to tune a model, but it's even better to tune an entire pipeline. Why is that? Because you might want to tune some of the pre-processing parameters and not just model hyperparameters, okay? So how does it work? Well, first we specify the parameters we want to search and what values to try for those parameters. The tricky part here is that you have to specify the step name and the parameter name. So the name of the first step in the pipeline is ColumnTransformer. The name of the first transformer in the ColumnTransformer is CountVectorizer, and the name of the parameter within that we want to tune is MinDF, and we put 2 underscores between each of those, okay? The name of the second step of the pipeline is Logistic regression, and we want to tune its C parameter, and then again, we want to tune the penalty parameter. And for each of these things, we are telling it, here are the values I want to try, okay? Now, as far as how did I know which values to try, what parameters to tune, you can figure that out through some research and some experience, but it's not super obvious what to do and how to do it really well. Okay, so let's set up our grid search. So we import grid search CV, we create an instance, we pass the pipeline to that instance, we pass the parameters, and then we do grid.fit, which does the actual search. Now, grid search CV tries all possible combinations of these parameters. So it will run 5-fold cross-validation, 2 times 3 times 2. So 12 times it will run 5-fold cross-validation. And there are lots of ways to look at the results, but usually you just want to know what's the best score it found. And it's 0.822. Which is better than the 0.802 that we saw without any tuning. And then we also are going to look at the parameters that produce that best score. And here they are, the MinDF of 1, a C of 10, and a penalty of L1. Now those, if we were satisfied, those are the parameters we would use when making predictions because we believe those to be the best. Okay, I know that was a lot. This is not, what I've just outlined is not a perfect process. It does have some weaknesses, but overall, this is super useful to do and know how to do. Tip number 17. Grid search CV taking too long. Try randomized search CV with a small number of iterations. Make sure to specify a distribution instead of a list of values for continuous parameters. Okay. Let's take a look. So our setup is we've got a pipeline of CountVectorizer and multinomial naive Bayes, which is a model. Just like we saw before, we can cross-validate the pipeline. These are different sets of features, by the way, so don't compare it to number 16, but this was 0.800. If we were going to use plain vanilla grid search, it would try all possible combinations of all parameters. So let's pretend in this case, I wanted to try 4 values for MinDF, 2 values for lowercase, and ignore this for a second. Let's pretend we wanted to try 10 different values for alpha, 0.1, 0.2, 0.3, 0.4, etc., all the way to 1. So if we were using grid search would run cross-validation 80 times because 4 times 2 times, let's pretend 10, is 80. Now, it's 5-fold cross-validation, so the model fitting would run 400 times. And if it's a slow-to-fit model, which is not the case here, but let's pretend, if it was a slow-to-fit model, grid search might run way too slow. So what do we do instead? Well, let's try randomized search CV. You tell it how many times you want to run, 10 in this case, and it will pick out random combinations of the parameters and try those 10 times. And it did indeed find a better score than above, just a bit. At this point, you might be thinking, this is weird. Why don't I try all the combinations? Why would I want to do a random search? Like, that seems suboptimal. Well, here are 2 things I love about randomized search. Number 1, you control the computational budget explicitly. So let's say you ran randomized search CV and put n iter equals 1, and it was a slow model, so it took a whole minute to run 1 iteration of 5-fold cross-validation. That is super useful information because then let's say you are going to lunch and you know you'll be back in 30 minutes and you want to tune your model while you're away from your desk. You can just set n iter equals 30 and you'll know that when you get back from lunch, it will have tried 30 combinations and it'll be finishing right when you're getting back. Grid search, on the other hand, it's very difficult and it's really not worth your time to try to figure out how to make it run the exact amount of time you have. And I know that sounds trivial, but it's really convenient sometimes not to say like, okay, I'm going to run my grid search. Should I come back to my computer in 5 minutes or 5 hours? What you do is you run it once with randomized search, and then you decide, okay, how many combinations do I want to try? Okay, so that's one reason I love randomized search. Here is the second reason. Sometimes the optimal parameters are in between the evenly spaced grid that you might choose. So this is exactly why we specified a distribution for the only continuous parameter, which is this alpha value. So for example, if you were tuning alpha with grid search, you might specify 0.25, 0.5, 0.75, and 1.0 for alpha. But what if the optimal value was at 0.4? Grid search will have no chance at finding that 0.4 value, but randomized search at least has a chance to find that value since you're specifying a distribution. Now, in this case, we specified a uniform distribution from 0 to 1, and the best value it found in this case was 0.198. Final note, it can be a bit tricky to figure out how to use SciPy to specify these distributions. If you can't figure out how to do it this way, you could just use np.linspace or np.logspace to create a big list of values to try within a range. Tip 18. Hyperparameter search results from grid search or randomized search can be converted into a data frame. It makes it far easier to explore the results. So, in the two tips above, we've just been looking at those best score and best params. In this case, what we're going to do is we are going to take the CV underscore results underscore attribute, and that's actually designed to be converted into a data frame. So we're going to convert it into a data frame and select out the 3 most relevant columns and then store that as results. And now that it's a data frame, you can explore it easily, and in this case, we're just going to sort it by rank test scores. Now, when you're doing this, you might be looking for certain trends like, oh, L1's always appearing above, or it's working well when we're using L1 regularization and C is high, but it's also working well when we're using L2 and C is low, or something like that. I'm just making things up. But you might be looking for trends that will help to guide your future testing. A couple things worth noting. Number one is I didn't show the pipeline here because I'm trying not to show an extreme amount of code in every tip, but I created this pipeline using the pipeline class instead of the make pipeline function. If I had used make pipeline, the default step name would have been logistic regression, and it makes for these really long parameter specifications like logistic regression underscore underscore penalty. And because I use the pipeline class, I can define the name of the step, and I just called it model, so that makes these a little shorter. If you want to see everything I'm talking about, you can look up this tip on GitHub. Now note, if, as you might kind of figure, let's say you have a bunch of parameters, not just 2 parameters you're trying, this area under params will quickly overflow and you won't be able to see everything. If that happens, what you'll want to do is just save the full data frame. Don't save only 3 columns from the data frame. Save the full data frame, and then you'll be able to examine the results on a parameter by parameter basis. And it's hard to explain exactly why, but you'll figure it out as soon as you look at the data frame of grid.cv results. Tip 19. Some important tuning parameters for logistic regression. We've got C, inverse of regularization strength, penalty, type of regularization, and the solver, which is an algorithm used for optimization. And here's a little comparison table of the solvers that I pulled from the scikit-learn documentation. So Why did I create this tip? Well, people often ask me, which parameters should I tune for a given model to improve performance? And that is an excellent question, and it's not a simple question to answer. Knowing that requires both research and experience. Often the scikit-learn docs will have some good advice, but I just wanted to mention a few parameters that I focus on when tuning logistic regression, which is my first choice for any classification problem. So let's start with C. Logistic regression in scikit-learn is regularized by default, unlike in stats models, for example. And briefly, if you're not familiar with regularization, it's a process that constrains the size of the model coefficients. So you use regularization to minimize a model's overfitting to the training data by reducing the variance of the model. In other words, if you believe a model is too complex, regularization will reduce the error due to variance more than it increases the error due to bias, resulting in a model that overall is more likely to generalize to future data. Anyway, you don't really have to know that to tune C. All you really need to know is that C is a floating point number, it's 1.0 by default, and you increase regularization by making the number smaller. Usually you'll tune it in powers of 10, like 0.01, 0.1, 1, 10, 100, etc. So that's C. Penalty is the type of regularization. So it's L2 regularization by default. The other options you can use for regularization are L1 and elastic net. Now, L2 is the type used by ridge regression, if you've heard of ridge regression. The L2 norm, it shrinks coefficients, but they remain non-zero. L1 is used by lasso regression, or the lasso as it's known, and L1 regularization does shrink coefficients to zero, which is why L1 regularization is used as a form of feature selection. And then elastic net is a combination of L1 and L2, and I usually don't use that, but it's worth noting. Okay, other thing you can tune is the solver. I mean, there are many more things you can tune, but this is an important one. The solver is the algorithm used to solve the optimization problem of calculating the coefficients. In other words, given a set of features and a target, the solver figures out what coefficients should be used by the model. Now, each solver has different strengths and weaknesses, it has different properties, and it will come up with different results. So it is actually worth trying different solvers. So my recommendation is you look at this chart, you read the documentation to decide which one to use for your particular problem and your particular hardware, and maybe just try each one at least once. You're probably not going to tune your solver with a grid search because they don't all support the same options. For example, LBFGS is the new default in scikit-learn, I think 0.22. LBFGS does not support L1. LibLinear does support L1. So the point is, I wouldn't usually put solver in my grid search. I would put C and penalty in my grid search. Regarding solvers, if you're getting warnings about convergence, then yes, you can try to get it to converge. Usually it's just easiest to switch solvers rather than trying to get a solver to work better. These are just some parameters you can tune. There are others you can tune for logistic regression and different ones for every single model, but these are the ones I think about first for logistic regression. Number 20. New in scikit-learn 0.22, plot a confusion matrix in one line of code. It's highly customizable. So here is our example. What is a confusion matrix? It is a tool for evaluating the performance of a classification model. So let's walk through the code. We're going to do a train test split, create an instance of logistic regression model, and fit our model to the training data. Now you are ready to plot already. You use plot confusion matrix, which I imported up here. You pass it a fitted model, X test and Y test. And then I also throw in some options that I'll mention in a moment. But let's talk about what the plot confusion matrix function does. you're passing it your fitted model. When you pass it xtest, it's going to run clf.predict on xtest, and then it's going to compare those predictions to y-test, and that comparison is the basis of the confusion matrix. You'll notice that nowhere in our code did we write clf.predict xtest because plot confusion matrix took care of that for us. In terms of the optional arguments, I passed in a matplotlib color map because I thought the default color map was ugly, and then I changed the values format. The values format is what's called a format specification string, which are super confusing in my opinion, but really useful. And by default, it was using scientific notation after just 2 digits, which was annoying for this 122. So I changed it to 3 digits, though in retrospect, I should have just used D here, which would have accomplished that in a more elegant way. And actually, D will be the default in the next version of scikit-learn 0.23. There are other ways you can modify the look of this confusion matrix, but those are the ones I just thought of immediately. A couple other things. If you store the return value of plot confusion matrix, you can access this attribute, which is the normal confusion matrix. And when you see that, you're reminded of how plain it looks and of how annoying it was to remember what each of these numbers represented. Wait, what is that 48 again? Whereas up here, you can see, oh, these are predicted labels 0 and 1. Here are true labels 0 and 1. Final note, you can actually pass a fitted pipeline, not just a fitted model, but a fitted pipeline that ends in a classification model to plot confusion matrix, and that will work as well. Tip 21, easily compare multiple ROC curves in a single plot. Automatically displays the AUC as well. Let's scroll down to the ROC curve. So the ROC curve is a tool for visualizing the performance of a classification model. It's a plot of true positive rate versus false positive rate across all possible discrimination thresholds. So it used to take a bunch of lines of code to make an ROC curve in scikit-learn, but now you can do it in one line of code, this plot ROC curve, and you can put multiple ROC curves in a single plot without too much work. In terms of the code, you can see that I fitted a model to xtrain and ytrain, and then to the plot ROC curve function, I passed the fitted model, xtest and ytest. It does the calculation of the predicted probabilities of class 1 for each sample in xtest, and then it compares those probabilities to ytest in order to plot the ROC curve. Thus, you never even have to call the predict proba method because that's done under the hood. Now, all of this is very similar to the plot confusion matrix function, which was tip 20, in that you also pass that a fitted model, xtest and ytest, and it does the rest. Now, finally, you'll note it displays the AUC for each model in the bottom right corner. AUC is area under the ROC curve, which is the single number summary of the ROC curve. Tip number 22. Did you know that there are 2 types of pipelines? The pipeline type determines which methods you can use with it and what those methods actually do. So this is a bit of a technical topic, but I think it's important to understand what a pipeline is doing for you if you want to get really good at scikit-learn. So the basics is there are 2 types of pipelines, and a pipeline can have any number of steps. Every step except the last must be a transformer, and the last step can be a model or a transformer. So pipelines that end in a model, I'm calling type 1, and pipelines that end in a transformer, I'm calling type 2. So with a type 1 pipeline, you use the fit and predict method, and it encapsulates all of the calls to fit, transform, and transform. But the important part here is that when you call fit, pipe.fit, it runs fit underscore transform. And when you run pipe.predict under the hood, it just runs transform. And that's important for many reasons, including preventing data leakage. So type 2, again, ends in a transformer. For example, an imputer followed by a one-hot encoder would be that type of pipeline. So if you run fit transform on this type of pipeline, all of the steps run fit transform. And if you run just transform, all of the steps run just transform. Tip 23. How do you display the intercept and coefficients for linear model? Well, they are stored as attributes of the model, and attributes end with an underscore if they are set during fit. This is just a simpler tip about how to display the intercept and coefficients. This applies to any linear models in scikit-learn, including logistic regression, linear regression, and many others. So anytime after the fit step, if you examine a model object, you will see attributes ending in underscore, and those are attributes that were set during fit. That's, of course, where you look to find the intercept and the coefficients. And this is just a reminder that scikit-learn models are not black boxes. You can inspect them to learn what they learned during model training. At the bottom here, I showed the feature names alongside the coefficients. This is dependent on you having a list of features that you stored earlier in your code. Now, someone mentioned on LinkedIn that this might even work better as a pandas series in which these are the values and this is the index, and I like that idea a lot. Tip number 24. This is one of my favorites so far. So one of the reasons people use decision trees is because of their high interpretability, and to interpret them, you have to visualize them, which is the point of this tip. So 2 new functions in scikit-learn 0.21 for visualizing decision trees: plot tree, which uses matplotlib instead of graphviz, and export text, which doesn't require any external libraries. So let's scroll down to the tree. In previous versions of scikit-learn, if you wanted to visualize a tree, you would have to use graphviz. And graphviz was a pain to install, and even when you got it working, it was a bit of a pain to use. You would run some Python code, it would output a file, you would leave Python, go to the command line, and convert it to a different file type, and then you could look at it. So plot tree, which is what I'm using here, is better in 2 ways. It only uses matplotlib, and the tree appears directly in your notebook. So let me briefly explain what you are looking at if you've never visualized a decision tree. So each box is a node. There are 3 internal nodes and 4 leaf nodes. The internal node is everywhere there was a split. So it tells you at the top the rule that was used to split that node. And the way it works is if the rule is true, you go left. If the rule is false, you go right. We see the Gini impurity before the split, the number of samples before the split, the classes of those samples before the split, and the majority class in that node. So in this data set, sex of 0 is male. So if male, you go left. If female, you go right. Now that split was chosen by the tree to maximize the decrease in impurity, meaning the goal of the split is to increase the node purity. So below it, in these boxes, you'll see the new Gini impurity, the new number of samples in that node, the class proportions within that node, and the majority class in that node. And you can see that the Gini impurity has decreased in both of the boxes below. And then these boxes, these nodes split again, which is why they have another splitting rule to decide whether you go left or right here and left or right here. Now these leaf nodes are the same, except the tree has stopped growing, so there's no more splits, hence why there's no more rules listed in those nodes. The color coding you're seeing in all of these nodes is based upon the Gini impurity. Darker means more pure, which is ultimately what the tree is trying to achieve. This bottom right one is all white because it is perfectly split between the classes. Now, if you were to plot a regression tree, it would look very similar to this, except that you would see mean squared error instead of Gini impurity as the criteria for splitting. Final note is that this can only be used with a single tree, not an ensemble of trees like random forests. Finally, let's take a look at export text at the bottom, also new in 0.21. This is the same tree as this here above, just visualized in a different way. It, of course, does not require matplotlib. It doesn't include nearly as much information, but it is much more compact. Tip 25. New in scikit-learn 0.22 is pruning of decision trees to avoid overfitting. It uses something called cost complexity pruning, and you increase this value to increase the pruning. So trees easily overfit the training data, and you can control the overfitting with various parameters like max depth, but one more elegant way to control the overfitting is with pruning, and prior to 0.22, this wasn't possible. So you can think of pruning like a regularization parameter for trees. The default value, which I'm implicitly using here, is 0, which means there's no pruning. And you can increase this value from 0 to penalize tree complexity. And as you do that, you can imagine nodes being removed from the tree. So like most tuning parameters, you're trying to balance overfitting and underfitting. You want to prune the right amount, so you determine the right amount by cross-validation. Now in this particular example, the unpruned tree has 331 nodes, the pruned tree has 121 nodes, and by pruning, we slightly increase the cross-validation score. Now you don't normally look at the number of nodes. That was just for teaching purposes here. Tip 26. Are you using train test split with classification? Be sure to set stratify equals y so that class proportions are preserved when splitting. And this is especially important if you have class imbalance. Okay, let's take a look. We've got a demonstration data set with only 8 observations in it, and we're going to use train test split for model evaluation. I pass it x and y. I'm going to set a test size of 50%, which is just for demonstration purposes. Normally you wouldn't split 50-50, but the point is we've got 8 observations, and with a test size of 50%, we're going to split into 4 in train and 4 in test. Okay. This is not stratified, and I'll explain that in a second, but because it's not stratified, it happened that ytrain contains all 4 of our cases of not fraud, and ytest contains 2 cases of not fraud and 2 cases of fraud. In other words, our original data set, you can infer, had 8 observations, of which 6 are not fraud and 2 are fraud. And the problem is that 4 of them, when it got split 50-50, 4 of them that appeared in the training set are not fraud, and all of the fraud cases appeared in the test set. So not fraud is the majority class, and fraud is the minority class. So what is the problem in all of this? Well, the model is going to be trained on the training data, and because the training data has only one target class, it will have no opportunity to learn what distinguishes fraud type data from not fraud type data. Thus, it's only going to ever predict not fraud. Now, the result of this is that you are not going to get a realistic estimate of how the model is going to perform. Because remember, we're doing model evaluation, and the whole point is to get an estimate on how the model is going to perform on new data. So this is an example of not being stratified. So let's solve that problem with stratification. And so what we do is we add an argument stratify equals y, and that's the object y referring to this object, not a string y. And when you pass this, this preserves the class proportions. So you can see that now we have one fraud observation in each of the two data sets after the split. So Y-train is 25% fraud and Y-test is 25% fraud, and that's because 25% fraud was the presence in the initial data set. So this preserves class proportions, and using this will result in a more realistic simulation of how the model is going to perform on new data. So this is probably always a good idea to include stratify equals Y when you're doing train test split. It's most important when there is significant class imbalance, because that's when not being stratified will cause the most problems. Now, to be clear, what I'm showing you here doesn't actually solve the problem of class imbalance, which is, in brief, that a model needs a bunch of samples to learn from. And if most of your data set is a majority class and the minority class is really small, your model will have a hard time picking up the signal of what is a predictor of the minority class. So that's the general problem of class imbalance, and stratify equals Y does not solve that. All that does is make train test split give you a more realistic estimate of how your model is going to perform. It doesn't actually solve the overall problem of class imbalance. Tip number 27. Need to impute a missing value for a categorical feature? You've got two options. You can impute the most frequent value, or you can impute the value missing, literally that string, which treats it as a separate category. So let's take a look at our example. So we've got our data set, and it's just one feature called shape, square, square, oval, circle, and missing value. So we're going to impute our missing value. We're going to use simple imputer in this case. And because this is a non-numeric column, you can't use mean or median, but you can use most frequent, and you can use constant. So if you use most frequent, it obviously picks out square because that was the most frequent value. If you use constant, then you have to set a fill value, or you can use the default, but I use the string missing, and then you'll see what appears in your output array is missing, the string, not NaN, but a string. So before I compare these two approaches, I will say even after you do this transformation, you're still going to have to one-hot encode the data or some other encoding of your choice. But if you think this through, if you do most frequent, this is going to give you one-hot encoded 1, 2, 3 feature columns, right? Because there are 3 unique values. And if you use this approach, you'll get 4 columns once you one-hot encode from square, oval, circle, and missing. That's why I say this is like treating missing values as a new category, because once you one-hot encode it, then you will have 4 categories. So between these two options, I tend to like the second option. I've heard it recommended by people I trust. And to me, it makes more theoretical sense to do this, because really doing this and then one-hot encoding is like adding a missing indicator column. And if you aren't familiar with that, go back to tip 9. But I like that we're imputing something, yes, but we're imputing something that is really just a missing indicator. Now, imputation is a huge topic, so I'm not saying imputation is always the solution for missing values. You still have to think about the pros and cons, but that's beyond the scope of right now. Tip 28, want to save a model or pipeline for later use. Use joblib, and I've got a warning here. You must load it into an identical environment and only load objects you trust. So let's see our example. We've got a pipeline that ends in a model. So I'm doing a fit, and then I'm doing a predict. I get my predictions, and then I'm going to use joblib to save the pipeline to a file. So I'll import joblib, and then I'll dump it, which means save it to a file. And then this is the file name I'm using. This .joblib extension doesn't matter. You can use whatever extension, but I just use it to make it clear what type of file it is. And then it tells you the file name here. And then you can load the pipeline back from a file, and I called it same pipe. And you can use that same pipe to make your predictions, and you can see we get the same predictions. So this is very similar to Pickle. It's specifically optimized for storing NumPy arrays, which is what scikit-learn uses. So that's why joblib is more useful than Pickle for scikit-learn. In terms of those warnings, a pickled or joblibbed object can contain malicious code, so you should only load objects you trust. And you do need to maintain an identical environment. If you save this from scikit-learn 0.22 and Python 3.7.1 and so on, you need to have that exact same environment when you load the joblibbed object back. Otherwise, you might get different results. Tip 29. Want to vectorize two text columns in a column transformer. You can't pass them in a list, but you can pass the vectorizer twice and they will learn separate vocabularies. Okay, the background here is that most pre-processing steps in scikit-learn expect 2D objects, but count vectorizer, and it does bag of words encoding for text data, only accepts 1D objects. Now, what that means is that with a column transformer, you can pass multiple columns to one hot encoder, for example, and then it will one hot encode them separately and then stack the results side by side. So you could do that with one hot encoder, but you cannot pass multiple columns to a single instance of count vectorizer. So the thing I'm trying to address is, let's say you have two text columns, you want to count vectorize them, and you want to use both of them as part of your resulting data set for training the model. So what is our workaround? Your workaround is just to pass the same vectorizer to ColumnTransformer twice, and then in each one you name the text column you want to use. And it will indeed learn separate vocabularies. It doesn't somehow combine all the data. The ColumnTransformer, by its nature, will stack the results side by side. You can, of course, do this for as many columns as you like. It is actually okay to use the same object. You don't need to make like two instances of count vectorizer called vect1 and vect2. You can just call it vect, and each time it will kind of get reset. Tip number 30. There are 4 ways to examine the steps of a pipeline. So we've got a pipeline of one hot encoding and classification through logistic regression. We are fitting the pipeline and we want to examine the steps of the pipeline. It's a 2-step pipeline. Specifically, we want to examine the model coefficients. So there are 4 ways you can do this. The first way is to use pipe.nameSteps, and then you type dot and then the step name and then dot in the attribute. And we see that there were 3 features, and here are the 3 coefficients that logistic regression learned. And this is the method I use because you can autocomplete the step name and you can autocomplete the attribute name. Method number 2 is very similar to method 1, except you use this bracket notation. This looks pretty good to me. I like the look of this, but at least in my notebook, I can't autocomplete the attribute name, so I don't like it as much as this because it's nice to be able to autocomplete the attribute name. The third option, you actually can just leave out named steps, and I'm surprised this actually works, but it does. Again, you're just passing the step name here. And the fourth option is the most concise, and it refers to the step by position, meaning using step 1 instead of step 0, and then looking at the coef attribute. So this option is probably best for code you're going to throw away, since it's the least readable after the fact. Now, I did get one LinkedIn comment that I thought was useful on this particular tip. It mentioned that you could just say pipe -1, and then that will give me the last step regardless of the length of the pipeline, which is super useful if your pipeline ends in a model. You know that always to get to the model, you can just do pipe bracket -1. Tip 31. If you use cross-validation and your samples are not in an arbitrary order, shuffling may be required to get meaningful results. And here's how you shuffle. Okay, so let's talk about cross-validation. So normally, when you are using cross-validation, you probably pass an integer to cross-validation, namely CV equals 5, for example, to do 5-fold cross-validation. One thing you might not know is that that does not shuffle your samples when splitting. So in other words, if you have 100 rows, for example, in your X, and you use cross-val score with CV equals 5, then rows 1 through 20 of X will be in a test fold, while rows 21 through 100 will be in a training fold. And then the next time around, rows 21 through 40 will be in a test fold, and rows 1 through 20 and 41 through 100 will be in a training fold, and so on. So there's no shuffling going on. That is why you get the same cross-val score every time you run it, because there's nothing random about the cross-validation process. So the obvious question is, do you need to shuffle? Well, if your rows in X are in an arbitrary order, then no, you do not need to shuffle. Shuffling will make no meaningful difference. If the rows are not in an arbitrary order, then yes, you should shuffle. And one example of this is, let's say your data set is sorted by the target value. So let's pretend it was a classification problem, and all of the class 0 were at the top and all of class 1 were at the bottom, just because that's how your data set was sorted. That is an example where you definitely need to shuffle. So if you decide that you do need to shuffle during cross-validation, I'm going to show you how to do it. Now, let me just emphasize, if you are in a scenario where you need to shuffle, but you don't, you will get unreliable cross-validation results. If you're in a situation where you don't need to shuffle, but you do, well, that's fine. That's not a problem. So if you like, you can just always shuffle. There's one exception to that related to like time-based data, and I'm not going to get into that. But generally speaking, shuffling isn't going to harm things, and it will definitely help improve the reliability of your cross-validation scores if you have any kind of sorting in your data set. With that being said, how do you shuffle if you need to shuffle? Well, you use a cross-validation iterator, which is what these objects are, this KF and this SKF. Those are cross-validation iterators, and you pass those to cross-val score instead of an integer. And in the iterator, which is an object, you define the number of folds, whether or not you want to shuffle, and you set a random state. Now, you're usually using this because you need to shuffle, so I'm going to put shuffle equals true, and you set a random state for reproducibility, because once you're shuffling things, there's not reproducibility without a random state. Now, the next logical question would be, why are there two different iterators, a k-fold and a stratified k-fold? Well, k-fold is good for regression problems because it does shuffling, if you set it to. Stratified k-fold is good for classification problems because it also does stratification when shuffling. So what is stratification? That is when you preserve the class proportions within each fold. So what does that mean? Well, if your target value, your Y, is 30% class 0 and 70% class 1, then doing stratified splitting will try to do 30% class 0 and 70% class 1 in every single fold that it creates. So it will try to duplicate those class proportions when splitting, and that results in more reliable cross-validation scores. So you only use stratified k-fold for classification because it doesn't make sense for regression. Final notes, grid search CV also does not shuffle, but just like cross-val score, you can pass an iterator to the CV argument in order to do shuffling if you need it. And train test split, in case you're wondering, does do shuffling. Tip 32. AUC is an excellent evaluation metric for binary classification, especially if you have class imbalance. And new in 0.22, AUC can be used with multiclass problems, and there are two different strategies, one versus one, one versus rest. So let's talk about this. So AUC is an evaluation metric for classification, just like accuracy is an evaluation metric and many others. AUC is designed around binary classification. So the thing that's new is the ability to use it with multiclass problems, meaning classification problems in which you have 3 or more classes. So in this tip, I show you how to do multiclass AUC in 2 different ways. One is with train test split, and you have to say, like, you pass this multiclass argument, and you either say OVO or OVR. If you're using it with cross-val score, you're setting it in the scoring parameter, and you set it as ROC AUC OVO or ROC AUC OVR. So this is really tactical. This is how you do it if you need to do it. So the natural question is, what is 1 versus 1 and what is 1 versus rest? Well, because AUC is designed around binary classification, these are some different strategies for calculating AUC for multiclass problems. So 1 versus 1, what it does is it computes the AUC of all possible pairwise combinations of classes and then takes the average to output a single score. Meaning, if you had a 3-class problem and you do 1 versus 1, it will calculate the AUC of class 1 versus class 2, class 1 versus class 3, and then class 2 versus class 3. And then it will average those AUCs. 1 versus rest is a little bit different. It computes the AUC of each class against the rest and then takes the average. So that would be class 1 versus classes 2 and 3, class 2 versus the combination of classes 1 and 3, and then class 3 versus the combination of classes 1 and 2. So those are the 2 different strategies. If you've heard of 1 versus all, that is the same as 1 versus rest, though I find 1 versus rest to be slightly more clear in that it's a single class versus the rest of the classes. So I have not studied the pros and cons of 1 versus 1 and 1 versus rest, so I can't immediately recommend which is better or under what circumstances each of those is better. Just know that you do have to choose which you're going to use if you use AUC for a multi-class problem. Finally, I make this claim in the tip that it's an excellent evaluation metric, especially if you have class imbalance. There's always debate about what you should use for class imbalance. And I'm not saying AUC is definitely the best in all scenarios if you have class imbalance. I'm just saying it is well suited to class imbalance, and nothing I have yet read has changed my mind on that. But if I ever change my mind, I will try to let you know. Tip 33, want to do feature engineering within a column transformer or pipeline. Step 1, select an existing function or write your own. Step 2, convert it to a transformer using function transformer. And step 3, celebrate, of course. So what is this all about? Because for most people, this looks completely foreign because function transformer is not well known. So here is the background. If you are doing machine learning, it is optimal for you to do all of your data preprocessing within scikit-learn. Why would that be? Well, there are many reasons. I talk about them at length in my latest machine learning course, but here are some of the reasons to do your preprocessing in scikit-learn. Number 1, it prevents data leakage, and that's a big topic unto itself. I talked about this some in tips 4 and 5, so check those out if you want. Another reason to do your preprocessing with scikit-learn, well, that makes it easy to apply the same preprocessing to new data that you're going to make predictions for. And another reason to do data preprocessing in scikit-learn is you can tune all of your preprocessing with grid search. So if you are currently doing some of your data preprocessing in pandas and you want to move it to scikit-learn, the first thing you would do is look for a function purpose-built to do that. So if you're doing get dummies in pandas, you would use one hot encoder in scikit-learn instead. If you're doing imputation in pandas, you would use one of the imputers in scikit-learn, and so on. But if you need to use a custom transformation, there's a different way you'll have to do that. So basically, this tip is if you have some function that you want to do to pre-process your data before using it for machine learning, and that's not natively available in scikit-learn, I'm showing you how to do it in scikit-learn. And the process is taking a function and converting it to a transformer, because scikit-learn works with specific types of objects, and there are estimator objects, which are like usually models, and transformer objects, which do data transformations, okay? So if you have a function that's not available in scikit-learn natively, you can make it available to scikit-learn by converting the function to a transformer. And that's what function transformer does. It converts functions to transformers. So here are some examples. I've got this NumPy function clip, and I want to clip values from 100 to 600. I take the clip function and I convert it with these arguments into a transformer called clip values. In this second example, I take this custom function, which takes a data frame and applies string slicing, and I convert that arbitrary custom function into a transformer called getFirstLetter. And now that I've created those two transformers, I can put them in a column transformer just like anything else you can put in a column transformer, like a vectorizer or a one-hot encoder or an imputer or whatever, okay? So that's the power here, is being able to take any function, turn it into a transformer, put that in a column transformer, and now your column transformer can go in a pipeline, and all your feature engineering is being done in scikit-learn instead of pandas. And here's just an example of applying that transformation using the fit transform method. So we're clipping fair, and then we're extracting the first letter from code and dec. Tip number 34. It's simple to add feature selection to a pipeline. Step 1, use select percentile to keep the highest scoring features. Step 2, add feature selection after preprocessing, but before model building. And then I say make sure to tune the percentile. Okay, there's lots of ways to do feature selection in scikit-learn. There's select percentile, select k-best, select from model, etc. The point of this tip is that it's actually not hard to include feature selection into a pipeline. So we've got our first pipeline that just includes 2 steps, a vectorizer and a classifier. Then in my second pipeline, I include a vectorizer, a feature selection object, and then a classifier. And you'll notice that the first pipeline has this score, the second pipeline has a higher accuracy because of the feature selection. Now, what is this feature selection object? Well, it's a select percentile object where I define the statistical test, a chi-squared test, which is available within scikit-learn. And then I said, I want you to keep 50% of the highest scoring features as defined by the chi-squared test. So I put that in my pipeline, and magic, it gets better because it does feature selection. So you are probably having lots of questions. What test should I use? What percentile should I set? Should I use select percentile or select k-best or some other method? All of those are tough questions. There's no universal answer. In selecting a statistical test, I would read the documentation for advice. I like starting with select percentile because it's very simple. Do I want 1% of the features? Do I want 99% of the features? And I can tune that value in a grid search, which is the great part about doing feature selection in scikit-learn. Normally, for what it's worth, my first step in a pipeline will be a column transformer. And in this case, I just did a vectorizer and I only passed, I think, probably a single text column. That was just to make the example simple. But normally, my 3-step pipeline would be column transformer, feature selection object, classifier, or regressor. Scikit-learn tip number 35. There's no need to use dot values when passing a data frame or a series to scikit-learn. It knows how to access the underlying NumPy array. Okay, this is a simple one. So you'll see lots of scikit-learn tutorials that use the dot values attribute or the toNumPy function to convert pandas objects into NumPy arrays before passing them to scikit-learn. And all this tip is saying is this is not necessary with scikit-learn. Number one, when you do that, you're making your code a bit more verbose. You're doing one extra thing you don't need to do. But also, scikit-learn does understand pandas objects quite nicely. A column transformer can understand a pandas data frame. You can access columns by name if you pass it a pandas data frame. And furthermore, scikit-learn has improvements planned in which it will take more advantage of pandas data types. So the bottom line there is don't try to turn your pandas objects into NumPy arrays for scikit-learn's benefit. It will benefit more if you just pass it pandas objects. So this is tip 36. New in version 0.23, most parameters are now expected to be passed as keyword arguments. So they'll raise a warning if passed positionally and will error starting in 0.25. And we have our example. So previous to 0.23, you could pass arguments positionally. And so in this example, if you've got a SVC model and you happen to know that the first parameter is C and the second is kernel, you could just pass these values positionally. But it will raise a future warning. And instead, starting in 0.23, you now need to pass them as keyword arguments, which I'm showing down here, also known as named arguments. And the goal here is just to force you to make your code a bit more clear and unambiguous. Now, not all arguments have to be passed as keyword arguments. For example, with logistic regression, you can pass the penalty, such as L1 or L2, positionally. If you were using cross-val score, you can pass the estimator, X, and Y positionally. So the obvious question is, how do you know which arguments have to be passed as keyword arguments? Well, you just look at the class or function definition, either in the documentation or by using Shift-Tab in Jupyter, and everything after the asterisk you see has to be passed as keyword arguments, and everything before the asterisk can be passed positionally. Tip number 37, new in version 0.23, create interactive diagrams of pipelines and other estimators in Jupyter. You can click on any element to see more details, and you can even export the diagram to an HTML file. So if we look at this example, you'll see at the top of the code, I say set config display equals diagram. And this is how you enable this new behavior, which is, again, new in 0.23, but off by default. And then once you've enabled display equals diagram, anytime you print an estimator, you get this kind of diagram. And you can't tell from this video, of course, but this diagram is actually interactive. You can click on things to expand them and collapse them. And I've clicked on a bunch of things to expand them before taking this screenshot. So this new capability is most useful for pipelines because you can better understand the structure of the pipeline. However, this diagram functionality also works for column transformers, individual models, etc. Now, all of this only works in Jupyter Notebook or Lab. However, you can use this code down here to export it to an HTML file, and even that HTML file will have the interactivity built in. Now, one final thing you might have noticed is that in the diagram, only certain parameters are printed. For example, strategy equals constant for simple imputer. Those are parameters that have been changed from the defaults, and that's why they were printed. That is not a property of the diagram. That's a change of the default configuration in 0.23, and I'll discuss that a bit more in tip number 40. Scikit-learn tip number 38. Need to get the feature names output by a column transformer. Use get feature names, which now works with pass-through columns, which is new in version 0.23. So let's take a look at the example. Now, column transformer, which is what we're talking about, allows you to apply different transformations to different columns. So in this case, we've got 4 features. We're going to one-hot encode 2 of them and pass through the remainder, which is the other 2 columns. Now, pass through means just include them in the output unmodified. Now we do the fit transform, and that method does the transformation. It outputs 7 columns, and the obvious question is, what are the identities of those 7 columns? And what we do to find that out is use the getFeatureNames method of the ColumnTransformer. It shows 5 features output by one-hot encoder. The first 3 came from the first feature, which was embarked, and we can see that the categories in embarked were C, Q, and S. And then the other 2 one-hot encoded features came from the second feature we passed in, which was sex, and the categories that get output are female and male. The final 2 features out of the 7 were parch and fair, which were the columns that were passed through. So now we know the identities of the 7 columns. Now, previous to 0.23, getFeatureNames did not work with pass-through columns, so it's nice that it now does. There are still some limitations to getFeatureNames, namely that it doesn't work with pipelines that are within a ColumnTransformer. The core developers of scikit-learn are actively working through some different solutions to make it easier to retrieve feature names across all different scenarios, but it's actually a big technical challenge, so it might be a little while before that is available. Scikit-learn tip 39, new in version 0.23, need to load a toy dataset into a data frame including column names. You set as frame equals true. If you want features and target as separate objects, you also set return xy equals true. So let's look at our example. Now, this tip is only useful if you're loading up a toy dataset built into scikit-learn. Now, you might do this to test out some scikit-learn feature, or perhaps demo a feature to someone without having to load your own dataset. The API for this is a bit strange, but let's say you want a data frame with both the features and the target in it, okay? First, from the loadIris function, you will set as frame equals to true. Now that in itself causes the function to return a dictionary-like object called a bunch. You can get the data frame from the bunch by passing the frame as the dictionary key, and that returns this data frame object. And you can see from the output that we get a data frame. It has all 4 features from this iris dataset, and it includes the target column. Now, you might actually be interested in getting the features in a data frame and the target in a separate series. And to accomplish that, you also add on return xy equals true. So when you do this, so as frame equals true, return xy equals true, it returns a tuple, which we will unpack into x and y through assignment. And when we do that, you can see that x is a data frame with the features only, and y is a series, and it only has the target. Scikit-learn tip number 40, new in version 0.23, estimators only print the parameters that are not set to their default values. You can still see all parameters with getParams or restore the previous behavior with setConfig. All right, here is our example. So up here we create our classifier object, and we're changing 2 of the default parameters, namely C and solver. And then when we print it out, you'll see that it only prints the parameters that have been changed. So it just prints the C and the solver. And this is the new default behavior starting in version 0.23. Now, the idea here is that you mostly want to see the things that have changed rather than seeing all parameters. However, sometimes you do want to see all parameters, and in that case you use the getParams method, and here we see all the parameters. Now, if you don't really like the new default behavior, you can restore the prior behavior prior to 0.23 by using setConfig and setting print change only to false. And by changing that setting, now when we print out the classifier object, it will print out all of the parameters and their current values. Okay, scikit-learn tip number 41, new in version 0.23. Use drop equals if binary with one-hot encoder to drop the first category only if it's a binary feature, meaning it has exactly 2 categories. So let's take a look. We've got 2 unordered categorical features, also known as nominal features. And shape has 3 possible values. Color has 2 possible values. So we're going to use one-hot encoder to encode both of them numerically by creating dummy variables. And we're going to do this 3 different times and compare the differences. So first, we are going to use drop equals none, which is the default for one-hot encoder, and it creates 1 feature column per category. So thus, you can see that shape becomes 3 columns, and color becomes 2 columns. Next, we're going to use drop equals first, and that actually drops the first category in each feature. So shape, instead of becoming 3 columns, becomes 2 columns, and color, instead of becoming 2 columns, instead becomes 1 column. Now, this is allowed because when you use one-hot encoder, 1 column always contains redundant information, and so dropping it avoids multicollinearity. Now, I actually don't recommend using drop equals first, and I talk about why in tip 15, so you can go watch that video if you want to know more details. But in brief, number 1, there's usually no predictive benefit in dropping the first column of each one-hot encoded feature. Number 2, drop equals first is incompatible with handle unknown equals ignore, which is a useful option. And reason number 3, drop equals first is likely problematic if you standardize all features or if you use a regularized model, both of which are common. So again, you can watch tip 15 if you want to know more about that. Now, our third example here is what this tip today is really about. So we're using drop equals if binary, and this is what's new in scikit-learn 0.23. This drops the first category only if it's a binary feature, meaning a feature with 2 categories. So with drop equals if binary, shape is encoded as 3 columns, just like it was when using drop equals none, but color is encoded as 1 column, just like it was when using drop equals first. So what's the reasoning behind this particular option? I've read through all of the development notes on GitHub, and the justification for it was a bit fuzzy to me. It was something along the lines of it being most interpretable to remove a redundant column in the binary case, but not in the non-binary cases. So again, this is a bit fuzzy to me as to the justification for using this. If it's clear to you why you would use this option, definitely let me know in the comments, and I'd love to understand it better. As for me, I see drop equals if binary as having the same exact problems as drop equals first, so I'm going to continue to use drop equals none, but because you might see these out there in the real world, I wanted you to be aware of the impact of using each of these 3 options. Scikit-learn tip 42. In a column transformer, you can use the strings pass through and drop in place of a transformer. This is useful if you need to pass through some columns and drop others. Okay, so here's our example. First off, ColumnTransformer, if you've forgotten, is used to apply different preprocessing to different columns. So in this case, we've got our feature matrix X, and it has 5 columns, and our goal is to use simple imputer on column A to pass through columns B and C and to drop columns D and E. And when I say pass through, that means keep them in the feature matrix, but don't modify them. okay? So we're going to create our column transformer using make column transformer, and you pass it tuples. The first element of the tuple is the transformer. The second element of the tuple is the column or columns you want to apply it to. So in our column transformer, we're first going to do imputation on column A, and impute is an instance of simple imputer that I defined in the setup code that occurred before the code you're seeing. And then there's a special transformer you can use called pass-through, and notice that it's a string, not an object, and you can apply it to B and C. And this is just saying, I want you, column transformer, to pass through B and C to the output unmodified. And then the remainder of the columns, meaning any columns not specified in the column transformer, I want to drop those. So when we look at the fit transform, we see that A had simple imputation applied to that value right there, and then B and C were passed through, and then D and E were dropped. We're going to look at one other way to do this, which accomplishes the same exact thing, but in a different way. Again, we're going to impute column A. We are going to apply the drop transformer, which is another special transformer you can use, to D and E, and then pass through the remainder. And again, A was imputed, B and C were included due to remainder equals pass through, and D and E were dropped. So how should you choose between kind of these two ways of doing things? Well, if you have 2 columns to pass through and 100 columns to drop, then it makes the most sense to do this kind of format. But if you have, let's say, 2 columns to drop and 100 columns to pass through, then this is certainly easier. So in other words, you just want to use the option that is most convenient and readable. Tip number 43. With a tree-based model, try ordinal encoder instead of one-hot encoder, even for nominal, meaning unordered features. Accuracy will often be similar, but ordinal encoder will be much faster. All right, there is a lot in here, so let's start with some terminology. Nominal features are categorical features with no natural ordering. So I usually call these unordered categorical features. An example of this would be color, because there's no natural ordering of color. Ordinal features are categorical features with a natural ordering. One example of this would be shirt size. So there are categories like small, medium, large, extra large, but they do have a natural ordering. So when you have a nominal feature, meaning an unordered feature, you usually use one-hot encoding on it. This creates 1 column for each category. So if you have 10 possible values in a feature, one-hot encoder will create 10 columns. Now, if you have an ordinal feature, meaning an ordered feature, you will usually use ordinal encoder instead of one-hot encoder. An ordinal encoder creates 1 column for the entire feature. So with the shirt size example, you would tell ordinal encoder that the category ordering is small, medium, large, extra large, and it would encode small as 0, medium as 1, large as 2, and extra large as 3, and it would all be in 1 feature column. So these 2 different encodings, one-hot encoding for unordered features and ordinal encoder for ordered features, are usually the best way to provide categorical information to a model. In other words, they present the categorical information in a way that the model can best learn from. So that's the background to this tip. But what are we actually doing in this tip? Well, I've got this data set of 7 categorical columns. Now, they would all generally be encoded with one-hot encoder because they're unordered categories, except for education. You can likely make that an ordered category. So first, I'm showing you that with one hot encoder, if you applied it to those 7 features, you would create 60 feature columns. That tells us that there are 60 categories across these 7 features. So for example, work class, I happen to know, has 9 options, education has 16 options, marital status has 7 options, and so on. Ordinal encoder, when applied to these same features, creates 7 columns because each feature creates 1 column. So notice that I didn't provide any ordering information to ordinal encoder, so it actually just encodes them alphabetically. So what I'm doing here with ordinal encoder seems incorrect. I'm pretending that these features are ordered, and I'm pretending that the alphabetical ordering is the logical ordering. Okay, it seems incorrect what we're doing, but we're doing it anyway, and you'll see why in a minute. Then here we create an instance of random forests. This is a tree-based model, meaning it's made up of decision trees, and I'll tell you why that's relevant in a moment. Then we're creating a pipeline of one hot encoder and random forests, and we're cross-validating it to gauge the accuracy, and we're also using the %time IPython magic function to time the operation. It takes 23 seconds to run, and the accuracy was 82.6%. And again, these are unordered features, most of them, so one hot encoder makes the most sense. Now, in our final cell of this tip, I create a pipeline of ordinal encoder and random forests and cross-validate it. It takes less than 4 seconds to run versus 23, and the accuracy is within 0.1% of the one hot encoding. So what's going on here? Well, first of all, in terms of the time of operation, random forest just trains a lot faster with 7 features than with 60 features, and that's why it ran faster. Probably the more important point here is that the accuracy of ordinal encoder was basically the same as the one hot encoder. Now, how can that be? Because what we were doing with the ordinal encoder seems incorrect. Well, it turns out that tree-based models, such as random forests, can basically learn the same information from an ordinal encoded feature as from a one-hot encoded feature. And this is the case even if the features themselves are actually unordered. Now, this is a result of the way a decision tree learns, namely through recursive splitting of features. It's hard to explain this in more depth without teaching you an entire lesson on how decision trees are built and how they're ensembled. If you're familiar with that, it might make more sense to you as to why recursive splitting of features will allow it to learn from ordinally encoded features so well. Now, it's worth stating that a linear model like logistic regression would perform far better with one hot encoder than with ordinal encoder in this particular case. So let me step back and give you my overall recommendations. If you are using most models, encode your categorical features the conventional way, which is one hot encoder with unordered features and ordinal encoder with ordered features. But if you are using a tree-based model, you should try the conventional way, but then try using ordinal encoder for all categorical features. See whether the conventional way or just using ordinal encoder is more accurate. And if they're about the same, or especially if ordinal encoder is performing better, then just stick with ordinal encoder because it will be much, much faster. Scikit-learn tip number 44. Want your grid search to run faster? Set njobs equals -1 to use parallel processing with all CPUs. Okay, this tip actually looks complicated, but it is quite simple. This top part of the code is just the setup for the grid search of a pipeline. So we'll scroll down here. And then we'll actually do the grid search and use the %time IPython magic function to time it. And we'll see that the initial grid search takes 18 seconds. Then we'll come down here and we'll do the exact same search. We'll add the njobs equals -1 parameter, and it takes about 6 seconds. So what is going on here? Well, it turns out that some scikit-learn processes can be parallelized. By default, it will just use one CPU to do computations. But if you set njobs equal to 2, it will use 2 CPUs. And if you want to use all CPUs, you set it to -1. So this njobs parameter is not only available with grid search, but it's also available with randomized search and various other processes in scikit-learn that tend to be computationally expensive. For example, the random forest model has an njobs parameter that you can also set to -1. So the bottom line is, if you see an njobs parameter and you don't mind taking over all CPUs, then set it to -1 and things will generally be much faster. Now, a final note, if you're in a shared computing environment, you may want to actually find out how many CPUs are available and set it to an integer below that number. Otherwise, your process might interrupt everyone else's processes that are running on that machine, which might not be good. Scikit-learn tip number 45. Want to include feature interactions in your model? Use polynomial features. P.S. This is impractical if you have lots of features and unnecessary if you're using a tree-based model. Before we go through how you do this, let's first talk about why you might do this. So when you believe that there's an interaction between 2 or more features, one common technique is to create interaction terms, aka feature interactions, that your model can learn from. So this is generally done by multiplying the values of each pair of features and using those as new features. So this is useful when the combined impact of a pair of features is different from their individual impacts. So for example, let's pretend that you have features A and B and each have a small impact on the target, but when they're combined, they have a much larger impact on the target than you would expect. So in that case, it would be useful to create the interaction feature A times B, because the model can then learn that that interaction exists. So that's why you might create an interaction feature. In this particular case, we've got 3 features, A, B, and C, and we'll pretend we've decided to create interaction features between all of them. Our first step in creating them is to import the polynomial features class. We're going to create an instance called poly, and we're going to override some defaults. We'll set include bias equals false to avoid creating a column of 1s in the result, and interaction only equals true to avoid creating the square of each feature, which is the default. So when we run fit transform and pass it those 3 columns, it outputs 6 columns. The first 3 columns are A, B, and C. The next 3 columns are our interaction terms, A times B, A times C, and B times C. And if we want to include those feature interactions in our model, we would just include poly as one of the transformers in our ColumnTransformer. So the obvious question is, how would you choose which feature interactions to create? So the real answer is that you ideally want expert knowledge to guide your decision about interactions and which ones to create. If that's not available, you can explore the data and try to figure out which interactions make sense. And finally, if you have a small number of features, you could just create all possible interactions and then use feature selection to remove the ones that aren't useful. But, of course, with a large number of features, you can imagine that it's simply not practical to create all possible interactions. Couple final points. As I mentioned in this text above, decision tree-based models can learn feature interactions on their own through recursive splitting. This means that if you're using a tree-based model as your primary model, then you don't need to create feature interactions. There's no real point to doing this. However, if you're using a linear model as your primary model, you could actually use a tree-based model to discover interactions and then add those interactions to your linear model. Final point, as with any features you add to your model, you should use a model evaluation procedure to confirm that they are improving its performance before deciding whether to keep them in the model. Scikit-learn tip number 46. Want to improve your classifier's accuracy? Create multiple models and ensemble them using voting classifier. P.S. Voting regressor is also available. All right, let's take a look at the code. First, we've got a logistic regression model, and we're calculating the cross-validated accuracy by passing the model X and Y to cross-val score. It outputs an accuracy of 68%. Next, we've got a random forests model. We calculate the cross-validated accuracy with the same X and Y, and it outputs an accuracy of 69%. Finally, we'll ensemble the two models using voting classifier. I'll explain the code in a minute, but when we cross-validate the voting classifier, it outputs an accuracy of 72%. Thus, we've increased the accuracy by a meaningful amount just by using ensembling. So what is ensembling? Ensembling is the process of combining two or more models to produce a combined model, known as an ensemble, that is more accurate than any of the individual models. For a classification problem, the way ensembling works is that you can either let the classifiers vote on what class to predict, which is known as hard voting, or you can average the predicted probabilities output by the classifiers, which is known as soft voting. So why does this work? Well, the big idea behind ensembling is that if you have a collection of individually imperfect models, the one-off mistakes made by each model are probably not going to be made by the rest of the models. Thus, the mistakes will be discarded or at least reduced when ensembling the models. Another way of saying this is that ensembling produces better predictions because the ensemble has a lower variance than any of the individual models. So in this case, we ensembled a logistic regression model and a random forests model. Because their predictions are generated using completely different processes, they are likely to make different types of mistakes, and thus they're good candidates for ensembling. In terms of when you should use ensembling, it's useful anytime your highest priority is model performance. Keep in mind that ensembling does add a bit more complexity to your workflow, and the ensemble is also less interpretable than a single model. Now, going back to the code, we created the ensemble using the voting classifier class. We passed it a list of tuples, in which the first element of the tuple is a name, and the second element in the tuple is a classifier object. We used soft voting, which is usually better than hard voting if you have an even number of classifiers in the ensemble, and it works especially well if your models output well-calibrated predicted probabilities. However, soft voting requires that your models have a predict proba method, which not all models do, whereas hard voting will always work. Two final notes before we wrap up. First, if you have a regression problem, you would use the voting regressor class instead of voting classifier. Voting regressor simply averages the predictions made by the individual regressors, and so you won't need to choose a voting strategy. Second, you may be able to improve the accuracy of your ensemble even further by tuning the parameters of the ensemble itself using a grid search. And that is the topic of the next tip, which is tip 47. Scikit-learn tip number 47. Want to improve the accuracy of your voting classifier? Try tuning the voting and weights parameters to change how predictions are combined. P.S. If you're using voting regressor, just tune the weights parameter. Okay, in the previous tip, we talked about how you can combine multiple models using voting classifier, and the resulting ensemble will usually have a higher accuracy than any of the individual models. In this tip, we're going to see how to tune the parameters of the ensemble itself in order to increase its accuracy even further. Let's start with the setup. We're creating 3 classifiers, namely logistic regression, random forests, and multinomial naive Bayes. Then we'll ensemble the classifiers using the voting classifier class. When we cross-validate the ensemble, its accuracy is about 70%. Our goal here is to increase the accuracy of the ensemble even further. We'll do this by tuning the voting and weights parameters of the voting classifier. The voting parameter controls the voting strategy, which affects how the predictions of the 3 classifiers are combined. The options are hard voting, in which the classifiers simply take a majority vote, and soft voting, in which their predicted probabilities are averaged. Hard voting is the default, but as I mentioned in tip 46, soft voting will work better in many cases. The weights parameter controls how much influence each model exerts on the ensemble. By default, each of the 3 models is given equal weight, which is represented by the tuple of 3 ones. However, you can try weighting certain models more than others to give them more voting power when determining the predicted class labels or predicted probabilities. For example, we can give the logistic regression model double the voting power of the other models by setting the weights to 2, 1, 1. We put the various options for voting and weights in the params dictionary, and then we pass the voting classifier object and the params to grid search CV. We run the grid search, and it determines that the best parameters in this case were soft voting and a weight of 1, 2, 1, which means giving the random forests model double the voting power of the other models. By changing the ensemble to use those parameters, the accuracy of the ensemble has improved to over 72%. Keep in mind that we have not yet tuned the parameters of the individual models, such as the C value of logistic regression or the alpha value of naive Bayes. It's highly likely that the accuracy of the ensemble could be improved even further by tuning each model within the ensemble. This can be done as part of the same grid search, but when adding to the params dictionary, you will have to reference the model parameters using double underscore notation. For example, you would use CLF3 underscore underscore alpha to reference the alpha parameter of the naive Bayes classifier. One final note is that if you're using voting regressor instead of voting classifier, you will only tune the weights parameter, since voting regressor does not use a voting parameter. Scikit-learn tip number 48. Want to operate on part of a pipeline instead of the whole thing? Slice it using Python's slicing notation. Okay, this is a bit of an advanced tip, but follow along with me and I think you'll see how it can come in handy. We've got a 3-step pipeline in which the first step is a column transformer that does our preprocessing. The second step is a feature selection object, and the third step is a classifier. I've printed out the pipeline diagram, and you can see the same 3 steps: preprocessor, feature selector, and classifier. Now, back in tip 13, I talked about how you can examine a pipeline step by using the named steps attribute. For example, if you wanted to see the logistic regression coefficients, you could fit the pipeline, select that step, and then select its coef attribute. However, sometimes that is not enough. Sometimes you need to actually interact with one or more pipeline steps and run their methods. And that's what we're going to do in this tip. Here's our first example. Let's say you wanted to know how many feature columns are output by the first pipeline step, which is a column transformer. You can select the first step by using pipe bracket 0, and then run the fit-transform method on that step, and we can see that the output matrix contains 1,512 feature columns, which is what we wanted to know. This operation works because ColumnTransformer has a fit-transform method, and if you select this step only, you can run any of the ColumnTransformer's methods. Here's our second example. Let's say you wanted to know how many features were selected by the feature selection step. To figure that out, you would select the first two steps using Python's regular slicing notation, and then run fit-transform on that two-step pipeline. We can see that 756 of the 1,512 features were selected by the feature selection step. In case you were wondering, we passed both X and Y to fit-transform because the feature selection process requires knowledge of the target values. Here's our final example. Let's say you wanted to know which 756 features were selected by the feature selection step. To figure that out, you would select the feature selection step using bracket notation and then run its getSupport method, which returns a Boolean array of length 1,512. That array includes a true for every feature which was selected and a false for every feature which was removed. You could then use this array to filter down the 1,512 features and see which ones were selected. So those are just a few examples of how you can interact with one or more steps of a pipeline. Scikit-learn tip number 49. You can tune two or more models using the same grid search. Okay, before I talk about how to do this, let's step back and talk about grid search, how you normally use grid search, and why you might want to tune multiple models in the same grid search. Grid search is primarily used for tuning the hyperparameters of a model. You define what values you want to try for each parameter, and it cross-validates every possible combination of those parameters so that you can see which combination performs best. You can pass just a model to grid search, or even better, you can pass a pipeline to grid search. I demonstrated this in tip 16, but in brief, passing a pipeline to grid search allows you to tune the transformers and the model simultaneously, which can result in even better performance. In this tip, we're going to take this one step further. A pipeline can only contain a single model, so normally, if you want to try multiple models, you create multiple pipelines and then tune them separately. But it turns out that you can tune multiple models in the same grid search without creating multiple pipelines, and I'll show you how. Here are the three high-level steps, and then I'll walk you through the code. First, you create multiple parameter dictionaries. Second, you specify the model within each dictionary. And third, you put the dictionaries in a list. Let's take a look at the actual code. First, I've set up a column transformer, and this will become the first pipeline step. Next, I'm creating two models. CLF1 is a logistic regression model, and CLF2 is a random forests model. Each of these models will take a turn as the second pipeline step. Next, I'll create a two-step pipeline. The first step is the column transformer, and the second step is CLF1, but that's really just a placeholder, as you'll see below. Then we create a parameter dictionary specifically for CLF1, which is logistic regression. We're going to tune one parameter from the preprocessor step, namely the n-gram range parameter of count vectorizer, and two logistic regression parameters, namely penalty and C. If you've tuned a pipeline with grid search before, all of the code so far should look familiar. But this last line should look unfamiliar, and it's the key to this tip. We add one more entry to the dictionary to indicate that the classifier we want to use with this parameter set is logistic regression. Notice that this is a model object, not a string, and also notice that we put it in brackets to make it a list. This might seem strange, but it will make more sense in a minute. Next, we'll create a second parameter dictionary for CLF2, which is random forests. We'll tune one parameter from the preprocessor step and two random forest parameters, namely n estimators and min samples leaf. Just like above, we'll add one more entry to the dictionary to indicate that the classifier we want to use with this parameter set is random forests. During the grid search, this will override the logistic regression classifier we specified when creating the pipeline. Next, we'll create a list that includes both of these parameter sets. Finally, we pass the pipeline and the params list to grid search. When we run the search, it will first try every combination of parameters from params1 with the logistic regression model, and then it will try every combination of parameters from params2 with the random forests model. By checking best params, we can see that the best combination was a logistic regression model with C equal to 10, penalty equal to L1, and n-gram range equal to 1, 2. In the end, it's up to you to decide whether it makes more sense to tune all of your models using the same grid search as I've shown you in this tip, or to use a separate pipeline for each model with its own grid search. Scikit-learn tip number 50. Here's a simple pattern that can be adapted to solve many machine learning problems. It has plenty of shortcomings, but can work surprisingly well as is. Okay, before we talk about the shortcomings, let's go through the pattern. At a high level, what I'm going to show you in this tip is a pipeline that you can directly use, or at least adapt, to solve many supervised machine learning problems. This builds on top of what I've covered in a lot of other tips, so I'll mention those tips throughout this video. Let me scroll down so that you can see the pattern. This is a two-step pipeline in which the first step is a column transformer for preprocessing, and the second step is a logistic regression model for classification, though the second step could just as easily be a regression model for a regression problem. Almost all of the code you're seeing is for preprocessing, and the preprocessing code is split between numeric columns and categorical columns, so let's walk through that now. For the numeric columns, we're using simple imputer to handle any missing values. We'll impute the median rather than the default, which is the mean. We'll also set add indicator to true, which adds a missing indicator column to the output matrix and effectively treats missingness itself as a feature. You can learn more about add indicator in tip 9. We'll also set up a standard scaler in order to do feature standardization. This is useful because some machine learning models work best when the features are standardized, meaning they are centered around 0 and have a variance in the same order. For the categorical columns, we'll again use simple imputer to handle missing values, but this time we'll impute a constant string value. As I talked about in tip 27, this is basically like treating missing values as a separate category without having to set add indicator to true. We'll also set up a one-hot encoder to numerically encode these features using a one-hot encoding strategy. We'll set handle unknown to ignore rather than the default of error so that the encoder can handle categories in the new data that weren't seen in the training data. You can learn more about handle unknown in tip 7. So far, all we've done is set up 4 transformer objects. Before we assemble these together, we're going to set up 2 column selector objects. We'll use these objects in the ColumnTransformer to automatically select columns by data type so that this pattern can be used with any dataset regardless of its column names. The first column selector selects all numeric columns, and the second one selects all non-numeric columns. You can learn more about Make Column Selector in tip 2. Finally, let's assemble all of these preprocessing objects together into a single column transformer using Make Column Transformer, which I covered in tip 1. Make Column Transformer accepts tuples, in which the first element of the tuple is a transformer, and the second element of the tuple is the columns to which you want to apply that transformer. The first tuple handles all of the numeric columns. The transformer is a pipeline of median imputation and feature standardization, and that transformer will be applied to all numeric columns via the num_cols column selector. The second tuple handles all of the categorical columns. The transformer is a pipeline of constant imputation and one-hot encoding, and that transformer will be applied to all non-numeric columns via the categoricals column selector. And with that, we've got a single column transformer object that will handle all of our preprocessing. The final step is just to combine the preprocessing object and the logistic regression model into a pipeline using make pipeline. That's the end of this pattern, but I also added some code at the bottom just to demonstrate that the pipeline can be cross-validated and that it can be used to make predictions on new data. Note that I didn't include hyperparameter tuning, but you can learn about how to tune a pipeline in tip 16. Finally, let's talk about the shortcomings of this pattern so that you don't blindly use this pattern and assume that it will solve all of your machine learning problems perfectly. First, it assumes all columns have proper data types. If you've got a numeric column stored as strings, for example, this pattern will one-hot encode them, which is probably not what you want. It may include irrelevant or improper features. This pattern will use all of your columns as features, even columns that you know are not informative of the target, as well as columns that you are not even allowed to include because they leak information about the target. It does not handle text or date columns well. If you have a text column, you would probably want to use count vectorizer rather than one-hot encoder. If you have a date column, you would probably want to extract relevant features from the date rather than one-hot encoding it. Speaking of extracting features, it does not include feature engineering. Often, your model will benefit from you adding new features that don't natively exist in the dataset. Ordinal encoding may be better. We used one-hot encoding for categorical features, but ordinal encoding is likely better for any ordered features, as I talked about in tip 6, and it may be better for all categorical features if you're using a tree-based model, as I talked about in tip 43. Other imputation strategies may be better. We used simple imputer for missing value imputation, but you will often get better results by using KNN imputer or iterative imputer for numeric features, as I talked about in tip 11. Numeric features may not need scaling. We included a standard scaler in the pattern, but feature standardization is actually unnecessary for many machine learning models. A different model may be better. We only tried one model, namely logistic regression, but another model may work better for your particular data set. And there are probably other shortcomings of this pattern that I forgot to include. The point is that this pattern is a great starting point, but you'll want to carefully adapt it to your particular problem and data set. That's it for this tip. If you want to enroll in my free online course that includes all 50 tips, go to courses.dataschool.io, and there's also a link below. Thanks again for watching.